Electron counting in complexes. In the previous session that we have already studied the electron counting in complexes. There are two type of methods discussed, oxidation method and neutral atom method. Let us discuss this method with this example of platinum chloride, platinum tetrachloroplatinate. Here in neutral atom method, platinum contains 10 outermost shell electron, 4 chlorine atom supplies 4 electron and 2 minus charge supplies 2 electron. Totally PtCl4 2 minus consists 16 electron. But in oxidation state method, here the platinum is oxidized to platinum 2 plus and hence it loses 2 electron. So as a whole the net electron is 8 in the case of platinum 2 plus and 4 chloride ion supplies 8 electrons. Here there is chloride ions, ionic state. Here in this state platinum and chlorine in its ionic state. So it supplies 8 electron. Totally PtCl4 2 minus total electron is 16. And in the case of manganese 7 electron is there and 5 carbonyl group supplies 10 electron and hydrogen atom supplies 1 electron and HMnCO5 totally 18 electron. And in its oxidation state Mn is oxidized to Mn plus and hence it loses Mn plus. So there is net electron is 8 and 5 carbonyl groups supplies 2 electron each and total 10 electron. Hydride ion supplies 2 electron. Totally total number of electron is 18. Here there is a correction in this problem, and here the manganese Mn plus supplies 6 electron. Here the 8 electron is shown here. It is not at all correct. When Mn is oxidized to Mn plus, it loses 1 electron. So the manganese atom contains 7 electrons. So manganese plus ions contains 6 electron. 5 carbonyl group supplies 10 electron and hydride H minus ion supplies 2 electron. Totally HMnCO5 18 electron. Here in this there is a difference in neutral atom method and oxidation state method for counting the electrons. But the total number of electrons remains same. The way of counting electron is total number of electron is different in two methods, in neutral atom method and oxidation state method. But in the oxidation state method, the central atom and its ligand is the ionized state. So the number of electron will be different, but even though the total number of electrons remains same. This is a difference in between these two methods. And here is also the CO ligand is not alone its ability to function as a bridging group, and in addition to carbonyl group there are some other ligands like halogen or halide ligand bonds to can also act as a bridging ligand. Here this halogen ligand bound to a single metal atom has an additional electron pair, as it can contribute to a second metal center. This means that when this occurs, electron contribution of the ligand is increased by 2. In this here, if it is attached to a single halogen group, it can, in addition to bonding electron, there is also a pair of non-bonding electron is also present on the halogen atom. And when it is supplies this non-bonding electrons to, when it makes this non-bonding electron is also used for making bonding with a second metal atom. So it can act as a 3 electron donor as well as a 2 electron donor. Here is an example. 3 electron donor by the oxidation here in this scheme, in the case of RH2CO4 Cl2, there are 2 bridging chloroligands are present. And 3 electron, here the ligand can act as a 3 electron donor, and by the Osterschett method a 4 electron complex. In the 3 electron donor as well as 4 electron donor. In this electron, in both of this method, the total number of electron is 60. Here is the counting of electron in neutral atom method and Osterschett method is shown here. 2 rhodium atom supplies, one single rhodium atom supplies 9 electrons, so 2 rhodium atom supplies 18 electron, 4 CO 8 electron, 2 chlorine ligand, bridged chlorine ligand. Since it is a 3 electron donor, 2 chlorine bridged ligands are there, so totally 6 electron. So total number of electrons is 32. 32 for 2 rhodium atoms, so for 16 for single rhodium atom. 32 by 2, that is 16. And in the case of Osterschett method, rhodium is oxidized to RH plus, so the total number of electron is 2 electron is less, that is 16 electron. 4 CO supplies 8 electron, just as like neutral atom method. 2 chlorine bridge ligand, here the chlorine bridge ligand in Osterschett, since it is a chloride ion, so here it is in Osterschett method it can act as a 4 electron donor, and in neutral method chlorine atom acts as a 3 electron donor. So total number of electron is 8, and for the complex the total electron is 32 for 2 rhodium atom. For single rhodium atom it is 60. And that is the case, this means that not only the carbon group but also the halogen group can act as a bridge ligands. And depending upon the two methods, that is neutral atom method, whether it is an Osterschett method, the contribution by the bridged chloroligand will be different. In neutral atom method it is a 3 electron donor, and in Osterschett method it is a 4 electron donor. That is the difference. In addition to, there is also unsaturated organic ligands like allyl group, cyclopentadiene group, etc. can bind to metal, but their binding with the metal is different. In the case of allyl group, it can bind to a single metal atom, and also it can act as well as a 3 carbon atoms also bonded to metal atom. Here their naming can be written as eta 1 allyl, that is eta shows its hapticity. Hapticity means is the number of ligand atoms. It is the number of ligand atoms simultaneously attached to the central metal atom. Simultaneously attached to the metal atom. Here in the first case, in the case of eta 1 allyl group, that is shown the first figure. In this only one atom of the ligand can attach to the metal atom, so its hapticity is 1. And in the case of second structure, 3 carbon atoms are simultaneously attached to the metal atom, so its hapticity can be written as 3. So it can form eta 1 allyl group and eta 3 allyl, that is monohaptoallyl and trihaptoallyl. There are some examples of pyridine. In the case of pyridine group, eta 5, and it can also written as eta 3 C5H5 and eta 1 C5H5. That is depending upon the number of atoms of the ligand attached to the metal atom. There are 3 types of hapticity shown by cyclopentane ring. Here the power of 8 electron rule for predicting the structure of complexes involving illustrated in the for WCO2 C5H5 twice. In both these C5H5 ligands, there are 2 types of ligands are here. The tungsten atom is bonded to cyclopentane ring, as well as it can bonded to in a trihapto method also. That is pentahapto ligand is also present, and as well as the trihapto ligand is also present, and the total number of electrons remains 18. For tungsten 6, and from cyclopentane ring it is 5, and 5 plus 3 8, 8 plus CO 2 from each CO ligand, then 12 6 from tungsten, that is total 18 electron. So it can act as an 8 electron complex.